All right. Okay, so I'll go ahead and get started. So again, hi everyone. My name's Dr. Sam Bashara. I teach mechanical engineering classes here at CSU. And what I'm going to give you guys today is one of my favorite lectures. And this one, I'm going to try to keep it to about 25 minutes. Keep in mind, I normally would have about 50 to do this in class, but I think this will give you a good feel for the type of lectures that we do in our numerical methods course. And so when we talk about numerical methods, and actually, I would like to invite you to turn on. So I'm actually, the reason it looks like I'm kind of looking off to the side is I have all of your webcams set up on a little screen. So if you want to turn on your webcam so I can get a little visual feedback and maybe we can make this a little more interactive. Hey guys, that'd be really nice. I'd just like to see your faces, see how you're reacting and that sort of thing. So if you're comfortable, turn your webcams so it's nice to see your beautiful faces. All right, so like I said, today what I wanted to do is give you guys a little taste of MECH 105. So MECH 105 is a numerical methods course. You can think about this as computational mathematics. So how can we take math and then kind of turn it into a language that computers can speak? So what I want to get started off with is get you guys thinking about what is an algorithm. So what is an algorithm? I'm asking, unmute, let's talk. Let's do, this is how we do lectures, by the way, right? Lectures are not done in a vacuum. I don't just talk at the computer the whole damn time. So what's an algorithm? Someone unmute, tell me, what is it? No wrong answers. Well, unless you say it's like a car. It's not a car. What do you guys think? Anybody? You guys all too shy?
Isn't an algorithm like some form of math equation that you use just to help you that you put into a computer, and once you input a bunch of data, it comes out with an output?
Good. So Lainey, thank you for answering. So that is one form of an algorithm. But algorithms actually can get more generic than that. So you're right. That is what an algorithm is. So the way I'd like you guys all to think about an algorithm is it's just a set of instructions for solving a problem step by step. And let me share my screen so you can actually see what I'm doing, because I've actually been writing things and I just realized I forgot to share my screen. There we go. So now I think you can see does it look like there's like a whiteboard there? Can you guys see that? Okay. Okay, so what is an algorithm? So an algorithm is a set of instructions for solving a problem step by step. Now, what Lainey described was this exact same thing, except for a computer, but we use algorithms all the time, right? We use algorithms without even you realizing it. So for example, when you woke up this morning, you went through an algorithm to decide what to wear, right? You looked outside, said, oh, it looks pretty sunny. You checked your weather app. So you said, if temperature is greater than 50 degrees, wear whatever. So my algorithm went, if professor gives a lecture to students, wear dorky bow tie, right? Wear old man sweater, right? Those sorts of things. So I went through an algorithm for my morning routine, and everybody has these. So algorithms are not limited to the computer space. They exist in our daily lives. And if you investigate your behaviors, you'll start to understand that you're governed basically by algorithms. You are an algorithm machine. You make decisions about which grocery line to go into based off of which one has the longest line or the shortest line. Right? So you use algorithms all the time in your daily life. So to get you to think algorithmically, I like to talk about phone books, even though they're these ancient things that no one uses anymore. So let's go ahead and let's consider that we want to look someone up in a phone book. And actually, what we're going to describe today is the exact same way that your like cell phone does this. So even though I'm going to do it with I actually went and found one. There's a real life phone book. I don't know if there used to be like this thick, and so we're going to pretend that it's this thick for the sake of our argument. Do you guys know what a phone book is, by the way? Okay. We're rapidly approaching a date where people won't know what this is. So anyways, a phone book is a listing of all of the numbers in an area. And so it might be hard to see, but you can see there's just names. They're alphabetically sorted. They have phone numbers associated with them. So this is the X's or whatever. So they're sorted by last name. So I got a phone book here. And let's say that we're going to look someone up in the phone book. So let's say that we're going to look up my friend. I'm going to do Steve Johnson because, You guys probably met him this morning during the lab tours. And so I want to look at my friend Steve Johnson in the phone book. So this is what I'm going to do. I'm going to pick it up and I'm going to go, we're going to say that there's, just for the sake of argument, again, phone books used to be way thicker than this, but we're going to pretend there's 1,000 pages on this phone book, right? So we got 1,000 pages, and this is what I'm going to do. I'm going to open up my phone book, and I'm going to look for Steve. I'm going to go like this. I'm going to go page by page. Okay, well, he's not on that page. 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 So my algorithm for finding my friend Steve Smith is to flip through page by page until I find his phone number. Is this a good way to find Steve in the phone book? I guess maybe let me ask this question differently. Will I find Steve in this phone book? Sure, it works. This is what students tell me when they turn in their scripts. Dr. Bashara, it worked. Why did you mark it wrong? Well, I think we could all agree that although this algorithm works, it's wrong, right? It's not the right way to do it. So to kind of describe this, let's go ahead and I'm going to talk about a few different scenarios. So idea one was to flip through every page. Okay, and so if that's our first idea, let's go ahead and make a little chart here. We're gonna make a little chart. And on the x-axis, we're gonna say this is the size of the problem. So in this case, if this phone book has 1,000 pages and my friend Steve Johnson just so happens to be on the very last page, it's going to take 1,000 operations to find his number. So if the x-axis is the size and the y-axis is time to solve, this one is going to look like this. The example that I just described is going to look exactly like this, right? So it's going to be this nice linear line. If there's 1,000 pages, he's on the 1,000th page, it's going to take 1,000 operations to solve. So n. This is our idea one. All right, well, okay, we're smart people here. We could realize that that's dumb. So, this is what I'm going to decide to do. I'm going to go back to my phone book, and this time I'm going to speed this up 2 times. I'm going to make this 2 times faster. So this is what I'm going to do. I'm going to open it up, and now I'm going to go every other page. So I'm going to do 2 pages, right? I'm going to skip up in between. So there, boom, 2 pages, 1, 2, 2 pages, right? Does everyone agree that I've doubled the speed? This algorithm is 2 times faster. What's the problem with it?
You won't
Anybody?
find he's on one of the off pages.
Good. What do we call that in computer programming? You're right, by the way, that's correct. So the idea is that I've sped it up. It's 2 times faster, but it has a
% error.
There's an error, but okay, if you
let's
talk about this. What's that?
There's a hole, like
a hole. Okay, I see what you're saying.
Never mind. On a graph, but
okay, but what do we call this in computer programming? Our computer program has a. Oh, come on.
A problem?
It is a problem. What do we call? What do we call? If your program crashes, you say it has a. Nobody? A bug? Have you guys heard of a bug? No? Yes? Maybe? So that algorithm has a bug. So idea 2 was to go every other page. And sure enough, it is 2 times faster. It is. If we so happen to land on a page with Steve Johnson on it, it will be 2 times faster. So if we drew on our little graph here, we would say that, well, it's way, way faster. It's going to be n divided by 2, but it has a bug. Have you guys heard that term before, by the way, the terminology? Okay. So idea 2 is that it's 2 times faster. We're going to go every other page, but now it has a bug. So we're going to have to fix that. Okay, so we've been doing this a little bit ridiculously. What's the way that real humans do this? I got my phone book. Looking for my friend Steve Johnson. What do you guys recommend that I do? Here's the size of my problem, by the way. It should be like this thick, but phone books have gotten real skinny these days. So what do humans do? Yeah, go ahead.
And most phone books are normally probably alphabetized, so go to the S or the J and start looking.
Okay, so you're totally right, Mitchell. Correct. I need to, go to the S or the J, but I'm a really dumb computer. So one of the things that by the time we got to this lecture in MECH 105 that I would have convinced you is that computers are really dumb. We like to call them smartphones, but we should call them dumb phones because even though computers seem smart, you can think of them as just like the absolute dumbest thing on the planet. You can't tell someone dumb to flip to the S or the J. You have to be very specific about your instructions, right? So the way I like to describe this is imagine having someone that's so dumb that if you said, go get a glass of water, they couldn't do it. You'd have to say, walk to the kitchen, open the cabinet, take out a glass, put it under the sink, right? So like you have to be like, that's how you have to be with computers. So can anyone describe to me how I should find the S or the J if I was really, really dumb?
Well, you could have an input that says if this is not J, keep going, or this is not S, keep going. Such as if it's A, move to the next one, and if it's not S, then keep going.
Right, but that's going to be the same thing that's flipping page by page, but there's got to be a better way to do it. Right? Well, what does a human do? Don't I pick up the book?
Ooh,
Oh, go ahead.
you can try and start at like the middle of the book if it's in the middle of the alphabet and then keep flipping.
Exactly. Good. So this is what a human does. The human flips the book open to the middle. Boom. Now, what do? I need to make a decision. What letter is featured on this page, right? Then depending on that letter, I know that my problem then is either in this half of the book or this half of the book. So let's say that I flipped, remember it's Steve Johnson, so that's a J. And so let's say that I've opened the book to the middle and I've gotten to E. So I know for a fact he has to be on this side of the book. Does that make sense? So I started out with a problem that's this thick, then boom, I instantly make my problem. It's like, this is way more dramatic when this is super thick, but you get the idea. Now my problem's this thick. So I flip to the half of this part of the book, right? So now I see, okay, I've gotten to the R's. I know Steve has to be on this side of the phone book. Boom. Now my problem's this thick, right? And I continue this. Keep in mind, how many operations have I done so far? 2. Okay, I flip it open to the middle. I see Steve's in this half. Oh, I ripped up through the whole thing. Here you go. Boom. Steve's in this half. 3 operations. Are you guys with me? 4 operations. Maximum 6. That's it. The most operations I would take to find Steve, if I did it that method, would be 6 operations. Boom, he's on this page. Now my office has phone book pages all over it. So if we try to describe this algorithm in terms of an idea, so the idea is like idea 3, which we would call the human method, or maybe the real method, would be flip in half and then determine which half Steve is in. All right, this, if we tried to draw this on this chart, is going to be really fast. So we had this kind of N line, remember we had this N here, this kind of straight line here, and then we had this straight line here. Does anyone know, this is probably like a little too advanced, but does anyone know how I would draw what I just described, idea 3 on this? Does anyone know what it is?
Square root function.
Close. This is actually a logarithmic, so it would look like this. There's actually a limit. So depending on the size of that, there's a maximum number of operations. And we saw with that phone book, the maximum was 6, right? That was it. I did it, right? I did half flip. That was 6. That was the maximum number of operations it would take. So we've created so that this is a base 2 log 2n. So this is the beauty of this last algorithm. Let's go ahead and consider that the phone book doubles in size. So it went from 1,000 pages to 2,000 pages. So next year, phone book doubles in size. Idea 1 now takes 2,000 operations if our friend is on the last page, right? It went from 1,000 to 2,000 pages. If our friend is on the last page, it takes 2,000. Idea 2 is faster, but it still takes 1,000 pages. How many more, if we double the size of the phone book, how many more operations can we expect there to be maximum for that third algorithm? 1. That's the beauty. That is why this algorithm is what's used. It's insane, right? We doubled the amount of pages, and the most operations is going to take 1 more operation, right? That's why we have it every time. this is what I mean by thinking algorithmically, thinking like a computer. By the way, when you go into your phone book on your cell phone and you type in like someone's name and you see it pop up, right? I could try this real quick on my phone. So if I go to my phone, right, I'm going to my phone app, and you can see it there. And I'm going to type in like Steve, and you can see there's Steve Johnson's phone number. How did it find it so fast? It performed that exact operation I described. It flipped it in half, looked at the names, boom, boom, boom. That's how it works. This is how phone book apps for your phone work. They use this exact same algorithm. So again, the idea behind this is thinking like a computer. And if you were in class, what I would have you do now is I would have you draw a flow chart or pseudocode for how this algorithm works. And so a flow chart or pseudocode are just ways of representing algorithms in either English, that's what pseudocode is, or flow chart in terms of pictures. And these are kind of open to your interpretation. And so if you have some paper and pencil, I actually recommend that you follow along right now. Like, why not? It's kind of fun. So here we go. So if we try to draw, first let's start with the pseudocode for that algorithm. All right, so pseudocode again is just like an algorithm written out in plain English in a series of steps. So you think about your computer's this really, really dumb slave, right? And you can't tell it to find this name in the phone book. You have to be very, very specific. The pseudocode will just list out those very specific steps that you would give the computer. So here we go, pseudocode for this algorithm. Step 1, pick up phone book. Remember, this is a really, really dumb person. If you guys have you guys seen the movie Zoolander? So I'm not kidding. Whenever I write computer programs, I think of the Zoolander guy. I think of someone like really, really dumb. You know, someone that has like a gasoline fight kind of person. So you got to tell them, pick up the phone book, all right? So pick up the phone book. 2, open to the middle of the phone book. Now, step 3 is if Steve Johnson is among names, then you call Steve. So, right, so we have to tell our computer program, hey, we have to look for this name. And if we see this name, then you're done, right? You got to be very, very explicit with your computer. Okay, so if Steve Johnson is among the names, call him. Well, what if he's not? Well, we opened to the middle of the phone book. So first thing we do, we check, is Steve there? No, he's not. So what do we need to do? Well, we need to make a decision about, is he in the left half of the phone book or the right half of the phone book? So then the way we would say this algorithmically is we would say, else if Steve is earlier, and again, that might be a little bit hard for a computer, but we'll just kind of leave it at that for now. Remember, it's really, really dumb. So earlier is okay. You might want to say is less than or something, but we'll just leave it like this for now. We're going to say open to middle of the left half. And then we'll say go to line 3. 5 would then be else, oops, that's not else. Else Steve is later. So we need to open to the middle half, middle of the right half, and then go to line 3. And then we're almost done, but we're not quite done yet. I should have said else if, sorry. Else if Steve is later, go to line 3. Now, let me tell you a little story. So when I was a friend, or when I was young, I grew up in the Pacific Northwest. I grew up in Seattle. And so I lived near the Puget Sound. And so a lot of my friends that were, you know, very lucky had houses on the water. I didn't. But I had a friend who lived in a little town called Port Orchard, and he lived right on the water, so like right on the Puget Sound. And he had a dog, and you could not throw rocks into the Puget Sound, okay? This dog was like a golden retriever, beautiful, amazing dog. But the dumb dog, if you threw a rock in the water, it would swim out into the water and it would just swim in circles looking for the rock, right? This is how dumb this dog was. So we used to like, and so it's, of course, you know, the first thing he does, first thing I do when he tells me don't throw a rock in the water is throw a rock in the water. It's like, you know, I was a teenage boy. Like, you don't tell teenage boys not to do something if you don't want them to do it. So I throw a rock in the water. Sure enough, this dumb dog runs out there. We have to get in a rowboat, row out there, and drag his dog out of the water so it doesn't drown trying to look for this rock. Okay, why did I tell you this story, and how does it relate to this algorithm? What do we need to, I'm not done, by the way, right? This is not done. What do I need to tell this program to do? Anybody? Okay, here we go. I don't know anyone named Xander Smith. So I'm going to go on my phone. I'm going to go onto my phone here. I'm typing Xander Smith. Okay, it doesn't display anything. What did my phone do?
Else, you make like an else statement, no name found. The program does not understand.
Good. Or else the computer, this is what's called an infinite loop. So think about your dumb computer. If you said find Steve Johnson and there is no Steve Johnson, the computer just swims around that rock, right? The computer's a dumb golden retriever. If you don't tell it to give up, it'll just keep going forever. So the last bit here that we need to do is we need to say 6 is else give up. If you don't find Steve and you keep splitting the book in half and you get to the very end of those halves, you still don't find Steve, there's no half to flip to, you got to give up. So then 7, we would just say something like end. So this is our computer program that we just developed, right? And so this is an algorithm, and this is how you have to think, right? You got to remember that your computer's super dumb, right? You have to tell it to stop. You have to tell it to start. You have to tell it very specifically what processes to do. So I guess the last, I have about 2 or 3 minutes here. The last little bit that I just kind of thought might be interesting for you all is going over like a flow chart of this. And so just so you know, these are real programming techniques. This pseudocode here is not just for fun. In fact, if you talk to any professional programmer, they consistently do this type of thinking before they write their computer programs. This is real, right? Like if you go to some Apple employee's, notebook next to his table when he was writing the app for the phone app, he probably had sketched something like this out. Probably not. This is like a very, very commonly used algorithm. This is not like a total unique one, but you get the idea, right? This type of pseudocode is very, very common. In fact, before I became a professor, I worked writing algorithms for flow cytometers, which is a type of medical device, and all of us programmers did this. All of us. We all did something a little different. We all had our own little style, but something very similar to this, or flowcharts. So really quick, just because we've kind of beaten this phone book thing to death, let's just think of another algorithm. So how about let's say we wanted to make a pizza app. So we wanted to make an app where a person can order pizza from us. And so the flow for that program might look something like this. And so the flow chart we would do would look like this. And so we always use ovals for what we call terminators, not like the I'll be back kind, just like start and stop, not as fun. But anyways, terminators. So we start our program. Terminators are shaped like ovals. Okay, the first thing that we need to do is get the pizza size. Right? So we have our app. Well, we want to know what size pizza they want. So we draw inputs, outputs as parallelograms for flowcharts. All right, so we get our pizza size. Well, then we need to get, what toppings do you want? So we'll say get topping. All right, well, then we need to ask a question. So we do that as a rhombus. And so we'll say, any additional toppings? If the person says no, that evaluates to false, we can continue. If it's true, we need to go back here and get the toppings. So if they want more toppings, go ahead and enter it. You want another one? Go ahead and enter it. Want another one? No. Continue on. So then the last question might be, do you want any additional pizzas? Right? So maybe you're ordering 3. If the answer to that is yes, well, then we can go all the way back up to here. Oh, I forgot this was get pizza size, I think. Yep. So this is true. If they don't want any more pizzas, well, then what we need to do next is we need to calculate the price. We draw processes as rectangles. So when we're just calculating something or doing something like that, we draw it as a rectangle. And then the last little bit is we want to display the order to our customer. And then, we might just stop there. That we might have a few more complicated things. We might want to ask for confirmation and that sort of thing. But this gives you an idea of the type of flowcharting exercise, right? We start, get the pizza size, get the toppings, and then you can see how this program flows, right? So this is the algorithm that you might use for a pizza ordering app. All right, so that's a real quick, brief taste of MECH 105. Some of the ways we want you to think, right? The idea behind this is to get you to think algorithmically. So I'm gonna go ahead and stop there to give my colleagues some time to do their lectures. I think what we'll do is I'm gonna try to save a little bit of time at the end for questions. So if you have any questions, you can ask them at the end. Kirk or Bonnie, is one of you guys ready? So
yeah, I can go for it.
Okay. So yeah, go ahead. So I'll shut up and Bonnie will take it away. Here, let me stop my screen.
All right.
Okay.
Let me get my screen share going. All right. Hopefully you can see my screen now. I'm not sure that this lecture qualifies as my favorite of all time, but I wanted to present something that's a very important topic that can be easily digested in 20 minutes. So today I will introduce you to the concept of tolerancing dimensions, something that is critical to good design, but is often overlooked by the engineering novice. And I've shortened and combined a few lessons to give you a taste of the sophomore level course I teach called MECH 201, Engineering Design 1. Assemblies of piece parts is what makes up most engineered products. And a critical component of producing a good quality product is reliability. Reliability stems from accounting for manufacturing variability, which minimizes the likelihood of piece parts not properly mating. So without considering manufacturing variability in designs, our parts might not fit and or work properly, which can lead to product failure or worse, injury or death. Tolerances are used to control the manufacturing variability to a level that is still cost-effective, yet produces an acceptable level of reliability for the assembly and the functionality of the product. So the term tolerance is the total amount a dimension may vary from the ideal value for that dimension. In other words, tolerance is the difference between the maximum and minimum acceptable limits of a dimension. So take, for example, the manufacture of a piston ring, which are used in internal combustion engines like the one shown here, and they seal the combustion chamber among other functions that are listed here. They're very simple components in an internal combustion engine, yet they serve a lot of very important functions. And this table over here is a list of 25 piston rings that were produced using the same method. And for each of those 25 piston rings, we've taken 5 measurements of the internal diameter of the piston ring. And for these measurements, we can see that the diametric size varies not only on a single ring, meaning they're not perfectly round, but also among all of the rings produced. And plotting those measured results on a histogram of all those internal diameters, we can see that the nominal diameter for that ring is about 74. So that was the intended perfect size for the rings. But the deviation from nominal can vary as much as 0.035, although this is less likely to occur. We didn't measure this as many times as we measured what was around our intended size of 74. The concern is not that the piston ring diameter is imperfect. The concern is whether the ring will still fit and function as it should, As long as this range of values is within the tolerance limits set by the engineer, in theory, that means that the ring should perform as intended and there should be no issues. So variability in manufacturing is just a fact of life. It is impossible to produce anything exactly the same way every time. And any ideas where this variability in manufacturing comes from? Feel free to unmute and give your ideas. Why do you think it's impossible to produce a part the same way every time?
There's so many different variables to anticipate to build that one item.
And what do you mean by variables? What would we not be able to control in producing a part?
Each individual part has like each more individual parts, which each have their own different part of coding, and everybody codes differently.
Oh, you mean for like a CNC machine and setting up the, what do you mean by code differently?
I was mostly
Talking
just
like
kind of
machine
going
error.
back.
Let's see. So yeah, the manufacturing tolerances is what we're going to use to try to essentially limit the outcome for our parts and what the size of our parts will, a range of sizes that our parts might end up being once they get produced. That's where the tolerancing comes in. But what problems arise during manufacturing that we're not able to control, and therefore we're not able to perfectly control the outcome of the produced part? Yeah, so I'm just seeing comments here. Producing an item without a mold, it will be different every time. Even under mold considerations, if you're doing injection molding, you might have parts come out differently every time. They're not obvious, maybe differences, but once you look under close inspection, you'll see these differences, and they could matter to the performance of your product. But basically, manufacturing errors can be split up into two different categories. The first are called systematic errors or bias errors, which these have to do with faulty manufacturing systems, how you manufacturing the parts, the machines that you're using. And for example, instrumental errors, so this is includes wear of the tool, like imagine machining 10 of the same part. And the first time you machine the first part, your tool is very new and fresh, your cutting tool is very new. But by the time you get to that 10th part, your tool has been worn down and you can't get the same level of precision that you were able to with the first part you produced. So there's going to be differences among those parts because of that. Also, friction in the machine, aging of the machine that you use to manufacture, even consistent misuse of the machine can cause errors in manufacturing. And these systematic errors also include environmental conditions. So believe it or not, things like the temperature and the humidity of the room can affect the outcome of your produced part. Especially think of materials that might take in water. If you have a very humid room, then they've expanded, you're trying to machine them down, and then if the humidity leaves them and then their size is reduced further. And then we have random or precision errors. And these precision errors are the noise, quote unquote, in the system, which fluctuates seemingly randomly. And this could include user error. If you have different operators using the machines at different times, they have different levels of skill. And so they might end up producing the part to a certain quality, different quality. And it also includes environmental fluctuations, because throughout the day, the temperature, humidity, pressure in the room, it's all changing. and they could be changing quite rapidly and affecting the production of the part. So the main takeaway here is that there's no way to perfectly produce the same exact part every time. Instead, we must rely on proper tolerancing to guarantee that our parts are going to fit and function as intended. So let's look at how we actually tolerance on a drawing. Tolerancing dimension specifies the amount of acceptable variation that dimension can have. And the amount that each dimension is allowed to vary depends on the part function, assembly of the part, and the manufacturing process used to make the part. For example, if you're making parts for a jet engine, you're going to want to hold tighter tolerances, smaller allowed deviations for those dimensions than, for example, if you're making a bookshelf. So the problem is that a tighter tolerance is a much higher manufacturing cost for that feature of the part if you have a tight tolerance. Therefore, tolerancing is a balancing act between costs, making sure you minimize costs, while still ensuring that your product is going to function as intended. In other words, you have a reliable product that you're producing. So shown here are different ways to specify tolerances on dimensions. The first is shown in this box is unilateral tolerance, meaning that an acceptable deviation is only shown in one direction. We have 12 millimeters as our nominal value that we really hope we can produce this dimension on the part to, but we're saying that we can allow that dimension to go up as high as 12.1 millimeters, but it cannot go below 12 millimeters. So that's our tolerance on it. There's also bilateral tolerances where we specify an acceptable deviation in both directions. So for this 22 millimeter nominal dimension here, we're saying that we can allow this dimension to grow to 22.1, and we can allow it to shrink to 21.8. And so as long as the feature on this part that this dimension is controlling is between those two values, we're satisfied that whatever purpose this feature is being used for, it's going to function as intended. And then we have equilateral tolerances, which are, they're just bilateral tolerances that have the same deviation in both directions. And that's indicated by that plus minus symbol with the same level of tolerance on each side. And finally, you can specify a tolerance on a dimension by indicating the limits of size instead of a nominal value like shown here. Instead, we have the limits of the size of this dimension, high to low limits. And when you do something like this, instead of showing a nominal value like seen in these other dimensions, what do you think this is implying when you just give a limit to the size for this dimension? So it means that you don't really, for whatever reason, there's no nominal value that you're trying to target for this dimension. You truly don't care if the dimension is anywhere in this range. And so if the manufacturer ends up producing the parts towards the higher end of this dimension, it's not a big deal. Lower end of this dimension, not a big deal. There's no one particular value that the manufacturer is trying to hit every time. We of course we didn't always have this concept of tolerances, and before we came up with this idea of tolerancing our parts, every part that was designed had to be custom fit to its mating part. If only one part of an assembly failed, then in the best case scenarios, you would have to remake a custom fit replacement. Very costly and time consuming. And the worst case scenarios, you would have to scrap the whole assembly and make a new one. So imagine a world where even something as simple as a threaded bolt that, you know, you can go to Home Depot and you can buy a threaded bolt and you know it's going to fit every time to its mating nut. Back in the day, you had to make a custom threaded bolt and a custom mating nut to guarantee their fit. But early in the Industrial Revolution, all parts were handmade and assembled under this custom process, and every single part of an assembly was painstakingly adjusted to fit perfectly with its mating part. And typically, one business would be responsible for every part in an assembly because there was no standardizations like we have now, where you can buy stuff off the shelf and they're guaranteed to mate. Everything had to be custom made. And in today's modern world, different companies can make different parts. And thanks to tolerancing, we know that we can bring all these parts together and they will assemble without any issues and no adjustments needed. So that's the beauty of tolerancing. And today's modern concept of interchangeable parts started to take off around the beginning of the 19th century. Any ideas of what kind of demand spurred this innovation of interchangeable parts? Cars. I actually did not start with cars, but you can definitely believe, you know, Ford's Model T with modernizing that assembly line. A key component to that, right, was making sure that you could grab any part produced and know that you can fit it every time. It'll fit perfectly every time. Weapons, wow, you hit it. Yeah, it actually did. It started with being able to interchange parts in weapons, but particularly firearms, because unsurprisingly in war, every advantage counts. And with so many small and easily damaged parts, being able to replace a single one at a moment's notice really meant a difference between a military that was ready to fight at all times. So there are several factors that go into tolerance selection. And the first I want to talk about cost, and then we'll look at some other factors. When choosing the proper tolerances for your part, you must carefully consider every dimension of the part, keeping two main factors in mind. One is your design intent. What is the purpose of these dimensions? What are they going to do to the functionality of your product? And two, the manufacturing cost. How much is it going to cost to make that feature that you're trying to dimension right now? So let's just start with discussing what happens to the cost of a part when certain tolerances are specified. The cost of a part rapidly increases as tolerances are tightened. When I say tight tolerance, I mean that you're allowing less deviation in that dimension. For example, decreasing a tolerance from plus or minus 0.010 to plus or minus 0.005 inches can more than double the cost to create that part feature that has that dimension. So the increased cost stems from more time needed to machine to that tighter precision, and different machining operations needed to achieve that tighter tolerance, because as you request tighter and tighter tolerances, there might need to be additional machining operations to achieve it. And all that takes more time. Plus, in addition to that, the reject rate when you're doing your quality inspection of the part might increase. You might have to reject more parts because meeting tighter tolerances is less likely to occur on average. The required tolerance and manufacturing process must be carefully considered and matched to achieve the desired product quality at minimum cost. You, as the engineer, you cannot just simply demand the highest machining precision feasible for every feature of your part. Not only might it be difficult to achieve due to the machine you're using and or the material that the part is made out of, but it will definitely be cost and time prohibitive. It'll take longer to make and it'll be more costly. So take, for example, the machining of something very simple, this cylindrical steel shaft here. The graph that I'm showing here is the percent cost increase to manufacture this shaft versus the tolerance that we've specified on the diameter of the shaft. So the cost increase, as you can see, is exponential. So engineers must ask themselves, what is the loosest tolerance, the largest tolerance the shaft could have while still achieving the required functionality we need from the shaft? And there's definitely a lot that goes into answering that question, and I'll talk to you about that a little bit later in the lesson. It's important to know that each type of machining process can achieve a specific and limited range of tolerances. Shown here is a list of different machining processes. And then in the graphic, the typical achievable tolerance ranges for those types of machines. And of course, these are rough estimates of what these processes can achieve. The tolerance that a particular machine right in front of you can achieve will depend not only on what type of machine it is it a lathe, is it a mill, the grinder, what is it? But also the brand of the machine, the model, the maintenance and upkeep that's been done on the machine, the machinist's skill. All of these can affect what tolerances you can hold with the machine. So you, as the designer and engineer, should always be aware of the machining process used to make a part, feature. If a particular feature is not critical to the performance and functionality of the part, then you should always specify that tolerance for that feature at something that's easily achievable for the machine that's being used. So for example, if you're making a base plate for a TV stand, the tolerance on that base plate is really not important to the functionality of the TV stand. You know, plus or minus 10 thou is not going to make the difference versus plus or minus 5 thou. So what you should do is figure out what machine you're going to use to make that base plate, and then whatever tolerance is very easily achieved by that machine, you can specify it at that tolerance level. So hopefully, if nothing else, this information has made you realize the importance of considering costs associated with your design specifications. Never arbitrarily assign tolerances, and the specifications must be carefully considered and whenever possible, reduced to the most easily achievable values. So you're probably wondering, okay, so how do I know what specifications are appropriate for particular applications? And I think we have a little time left to briefly talk about design intent and how that leads to proper tolerancing. Design intent, so the functionality and the fit of your designs is what influences the tolerances that you need to hold on the design. Now that we know how much tolerances affect cost, we must be very deliberate in specifying those tolerances. Of course, the #1 priority of tolerancing is to guarantee our assemblies fit together and they function as intended. With any design, we must first identify the functional features of each part. What the functional features are those that are typically those that interact or come into contact with other parts. Often these contact points will be dynamic, meaning they're moving and during the operation of the product, and therefore they're critical to the product's performance. These functional features should always be dimensioned and toleranced first. Then finish dimensioning and tolerancing the remaining features that are not directly related to the successful functioning of the assembly. The non-critical features, those ones that don't really affect the functioning of your assembly, those should receive tolerances that are easily achievable by the manufacturing process used and to create those non-critical features. So for example, use the nominal tolerances for that specified by that manufacturing process for those non-critical features. Okay, let's look at this example shown here. This is a linkage bar that connects two shafts that are not shown, and each of which mates with a hole in this bar. One shaft goes through this hole, another shaft goes through this other hole. What are the critical dimensions for this bar? What features of this bar do you think matter most to the performance, the operation, the functionality of this linkage bar? Any ideas? Internal diameter of the holes, yes, that is definitely critical, because the way that they mate to the shafts is certainly very important. And the distance between the hole centers, another critical dimension to make sure that the functionality once the shafts are installed works as intended. Perfect. So those are our critical dimensions. They've been dimensioned in this left-hand view of the linkage bar. And what dimensions are not critical to the functionality of this linkage bar? Yeah, basically all the exterior dimensions of this linkage bar. We don't really care what the outside diameter is, or the thickness might matter a little bit, but not to a very high precision. The length of the bar, the overall length of the bar, not important. So those are the less critical dimensions. And therefore, when we're dimensioning this bar, we want to have these tight tolerances on the critical dimensions, 5/1000ths of an inch. We have tight tolerances. And then for those non-critical dimensions, we have looser tolerances, 5/100ths of an inch on them. All right. But you might be asking yourself, how do you know what tolerances are appropriate for certain functions that you need out of your product? Well, let's look at an example of that. Currently, both the part with the hole over here and the mating shaft are dimensioned to the same basic diameter. So in theory, what we want to do is have this shaft go into this hole. So far, all we've done is given the basic dimensions. But currently, we have no idea what the purpose of this assembly is, and nor what tolerances we would need to specify for that purpose. So if we were to give a machinist just these basic diameters, handed them a drawing with only these diameters on them, what are the potential negative outcomes when attempting to assemble the parts that you get back from the machinist? Yeah, so you might get the wrong type of fit that you wanted. And so one possibility of that is the shaft is produced to a significantly smaller diameter than the hole, which means that the parts can be easily put together, mated, but could be a problem if, in order to function properly, there should not be any play between the two parts, no wiggle room. So in other words, if the alignment of the shaft is critical to the functionality of your assembly, then having a big gap between the hole and the shaft is not optimal and might lead to failure during product operation. And another possibility is that the shaft is produced to a significantly larger diameter than the hole, and the two parts must be forcefully mated together, leaving no possibility that the shaft could rotate inside the hole after installation, which that could be very bad if the purpose of the shaft is to be able to rotate in the hole. So you might imagine it's impossible for us to tolerance these parts appropriately without first knowing the purpose of the assembly of these mating parts. So let's come up with a purpose. Let's say that the purpose of this shaft is to precisely locate a third mating part that's not shown here. But the third mating part will slide onto the opposite end of the shaft on this right-hand side of the shaft. And the third mating part needs to be properly aligned with another feature that's on the part with this hole, some other feature that we can't see right now. So in other words, the purpose of this shaft here is to align the part with the hole to another third part that's not shown. And knowing this, tolerances can now be selected from a standard for fits. Fit, the word fit means it's the degree of tightness between mating parts, how tightly mated they become. And there are standards that exist for different types of fits that you might want to achieve. So shown here are the selected tolerances based on a fit standard that would normally that I would normally teach you with this in this class, but we just don't have time to go into with this lesson. But this type of fit will allow the hole and the shaft to assemble easily. You're not going to have to force them together. But it will also be a close fit that doesn't leave any room for the shaft to move around, wiggle around in the hole. In other words, that would be a perfect fit for this particular application of being able to align different parts together using the shaft. So I think that's all we have time for today. And thanks for listening. And I'd be happy to answer any questions you might have. Well, if there aren't any questions, I'll hand it over to Dr. Bashar. Thank you.
All right, so well, yeah. So I guess let's just keep trucking along here. So Dr. McGilvray, you ready? Oh, you got your cool whiteboard thing. Okay, cool.
I'm ready.
Yeah, so I'll let you go ahead and fire away here. This thing's
All right, everyone. How's it going? Thanks for being here. This lecture looks a little bit better if you actually go to a speaker view. So in the top right corner, you should be able to hit speaker view instead of gallery view, and that might help expand the screen a little bit. I want this to be kind of conversational. So if you have any questions, just speak up or just type questions in the chat and I'll call on you, okay? So a little background about myself. I'm a mechanical engineer, obviously, but I'm a mechanical engineer from CSU, meaning I got my undergrad, my master's, and my PhD from CSU in the mechanical engineering department, and I am homegrown 100%. So what we're going to talk about today is one of my favorite lectures on one of my favorite classes, and that class is MECH 305. And this is machine design 325. So you take this when you're a junior or senior, and the purpose of this class is basically to give you an understanding of the stresses and strains that are inside machine components. So all we're going to do is just talk about the high level, what this class is generally the approach to it, and what we're going to do in that class. So my research is in the biomed field. So my example is going to be biomed driven, but in your mind, this can be any kind of machine or component that you're interested in. I mean, if you're interested in aerospace, it can be an aerospace component. If you're interested in traditional manufacturing, this can be a manufacturing component. So anything like that, okay? So imagine we have a component that we want to do analysis on and we want to redesign, design new, anything along those lines. So for me, I'm going to think of, in the biomed space, let's think of a prosthetic hand, okay? I think most people in the biomed, at least at the undergrad level, really like prosthetics. It's a robotics problem, it's a design problem, it's a programming problem, so it's very cool. So imagine we have a prosthetic, the end of a prosthetic finger. So we have a two component here where this, let's say this is your fingertip, okay? So, and here's a joint. So the finger right there, okay? So the question is, as mechanical engineers, how do we go about designing this? And specifically, let's say I want to integrate a force feedback sensor here into the fingertip, okay? Well, I can't do that until I understand the stresses and strains that are going to be imparted on this. So let's just think about what happens. You have a finger, it's grabbing. Let's imagine then if I grab something and it's delicate, I want this to be really high resolution. You like having good dexterity. So let's just say that there's going to be some pressure or distributed force applied at your fingertip. Okay. So this is some, let's just say, force over some distance x, okay? And then you're grabbing it, you know, it has a little friction in here. It's hard to pick up. It's a little heavy. So maybe it applies some type of moment on your finger. So we have multi-axial loading is what we have, okay? So the question is, how do I go about designing this? Not only what materials to design this out of, what geometric shapes to design this on, how thick to make the wall of this construct so I can embed my sensors in there, what kind of sensors I need, resolution. I mean, do they need to measure 1 gram, 1,000 grams, those kind of things? So what we would do then is we always start as the most simple design spaces we can think, and then we build complexity. So for me, how do I translate this? Well, this might look like, in my mind, like a very simple cantilevered component. So it may look something like that, all right? We've made some simplifications, some assumptions here, but that's okay. We're gonna get more complex as time goes on, okay? So we've taken our device and now we've simplified it to this, okay? And we may, you know, theoretically, we could be more complex and maybe add a hinge here, or a hole or stress concentration or what have you. But let's just start with this, okay? This is where we are in the design space. So let's just think about what we talk about in MECH 325. Well, it's all about stresses and how those stresses relate back to our component design. So how would we look at this? Well, in this class, we would learn that this moment, a moment is a force times a distance. And the formulations for the stress, force over area that this generates has a form of, say, sigma, that's stress in our world, is the moment times y being the distance from the neutral axis, so how far away we are from the y. So let's assume this is the neutral axis of our finger, so how far away our sensor needs to be from that neutral axis, and then it's a function of I. And this I is a function of geometry. So this is, I'm just gonna say geo. Okay, this is a function of geometry, all right? So we have this moment, we have these forces, and this force has a stress. Let's just say this generates some what we call shear stress. In our world, that's tau. And this, again, is a function. Let's assume it's round. Our fingers are round. It has some kind of 3/4 V over A. And this is area, okay? All right, so let's take a moment here. Stresses in our part are a function of the applied moments or forces, and a function of the location where we are in our component, as well as geometric concerns, whether that be area or I parameters. This is called the moment of inertia. We won't get into the details of that, but basically this is where we play as mechanical engineers. It is our responsibility to understand these stresses and how they relate to geometry and our applied loads and boundary conditions. So for example, this is a boundary condition, meaning I have fixed this in the wall. It's not allowed to rotate. It's my approximation for the finger here, okay? Is everyone following along? Yes, okay. All right, so now we have in this space, okay? So we can solve this. We can determine shear and moment inside this beam. That's kind of where we start in the class. But as we get more sophisticated, what we want to do is understand how these stress distributions actually behave inside our component. So let's just look at this one real quick. Our stress. So stress due to bending, this is causing bending. Hopefully we can appreciate that this force on the tip of our finger is causing this beam to bend up, right? Hopefully we can see that. It's trying to bend it up, okay? And if we think about what's happening here, let's imagine there's a very tiny fiber right here and a very tiny fiber right there, okay? As I bend this beam up, what is happening to this fiber? Okay, let's think about it. As this bends up, think about maybe a ruler or something that you've actually physically flexed. Well, this fiber becomes elongated, right? So if I'm looking, if this is my neutral axis, let's just draw that. Neutral axis means at the middle where it's neutral of our beam. We have the same area above and below, neutral. So these fibers down here are being stretched. So I'm going to draw that as a positive arrow, stretching those fibers. Now let's look at the fibers at the top. Well, what's happening to those? As we imagine this beam is being compressed or bent up, we're doing this. Well, these fibers are now in tension, okay? And what we know and what we'll learn in this class, we won't go into the details of the math behind it, but basically at this neutral axis here, there is no stress in bending. Meaning if I was to put a hole there, it would not be under stress because the stress profile kind of looks like this. It decreases towards the neutral axis. So this is intense compression. And then it increases as we go away. So this is the stress distribution. So this is sigma, okay? So interesting, all of a sudden as mechanical engineers, we realize that if I'm doing design of where I want to place my sensor, it matters if I put it on the tip, in the middle, on the top, due to this force, okay? This stress is also a function of geometry. So we have a lot of things to consider here, okay? Let's just look at this tau, this shear stress. So again, that has some kind of stress distribution. So again, let's do that as a function of, say, the middle part of our beam. Well, what that looks like, again, let's assume this is a circular cross-sectional area. It would look something like this. Where it's always in the same direction, but its magnitude changes with respect to depth. Okay, is everyone following? And again, if you have any questions, just speak up. We're just talking engineering here. I love talking engineering, okay? So we realize that there is different stress distributions as a function of applied load, as a function of geometry, okay? So how do we use that as a mechanical engineer to do design? Well, we continue with our complexity. So remember this, please, okay? So what we're going to see is that as we probe specific regions of interest inside our simplified beam, that we want to look at discrete ROIs. And the reason why we want to do that is because we want to build a map of the stresses inside our component, because those stresses, what we'll see in a moment, are what dictate if a part is going to fail or not, okay? I'm actually going to erase this too. Remember, we're talking about a hypothetical finger here that has loads on it. Okay. All right, so we have our beam. We understand that there's stress distributions inside that beam, okay? I'm going to draw it very small up here. This marker's running out. A moment and some forces, okay? So now we've discovered this, we know what's happening here. So let's get a little more complex. Now I want to understand what's happening, say, right here in my beam. So that may be right here, again, in our stress distribution, and right here, okay? That's where I want to put my attachment point for my sensor, or the sensor body itself, or something like that, okay? So what we can do is I can take this component, let's just blow it up for a second, and I can look at the stresses on this. So we're in here, so let's just say we have some tensile forces, okay? We have some shear forces, so I'm going to draw those like this. And what we'll learn is that these shear forces, they actually act on all faces, so they would have to be like this. Okay, and then I'm going to say, you know, depending on what's happening, we may also have some other loading that's causing, say, some compression. okay? So this is what's happening in our 2D space. This is a positive. This is a negative. So this is pulling this thing apart and this is pushing it. Basically just take away, it's a multi-axial loaded component, which is typical for almost all devices we look at, okay? So then the question is, how do I use this? Well, what I can do is I can understand, and this is my tau. These are my taus, shear stress, normal stresses. These are my sigmas, okay? Well, what I can do is I can convert this into what's called Morse circle, which I'll draw over here. So I have some positive shear stress. So that comes like here, let's say. And then I have some negative causing compression. And in this face, this is negative. So that's down here. Tau sigma. I'm not going to go into the details, but Morse circle is a tool we use in this class because it allows us to map what is happening to this specific element as it's rotated in this space. And why that's important is because here we have shear stresses and normal stresses, okay? That's great, but it's a little complicated to do some more sophisticated analysis down the road. However, I can rotate this element, meaning I can go from here to say, it's a pretty poor square, but I can rotate that such that I've simplified it that I only have normal forces on it. Whoop, like that, okay? So by rotating it, I haven't changed the loads or anything like that. I have just simplified the stresses on the component to make further analysis easier. So this is a tool we teach you in this class, okay, how to do this rotation. The cool part about that is that's what Morse circle is. So if here's my component here, this is my rotation. Well, now I can calculate these stresses, and these are called our principal stresses. And the cool part about this is once I understand Morse circle, what I can do is I can also instantly move into the 3D space, meaning this 2D representation, if I use Morse circle correctly, tells me what's happening in a 3D structure. So all of a sudden, I've just gone from our very simplified beam analysis of our mechanical finger into a 2D space, back into a 3D space, where now I have only very discrete individual principal stresses that tell us what's happening here. So what would that look like? Let's just say it would look something like this. Okay. I know it's drinking like drinking from a fire hose, but this is design. This is mechanical engineering stress analysis at its heart. We go simple, we build complexity. Okay. Again, if you have any questions, let us know. Nothing yet? Okay, cool. All right. So we've done all this work to understand the stresses now of the 3D stress space of my region of interest in my original device. Okay. Great, that's awesome. So we have the basic knowledge now of what's happening on our device, but how do we use that in design? Well, once I am playing in this space, what I can do is I can convert these are stresses. So I'm gonna call this, let's say sigma 3, sigma 1, sigma 2. These are our principal stresses. Well, I can take all of these and I can convert them into a variety of different stress formulations, but one of them we call sigma equivalent. And basically what this is, this takes all of these and boils it down to a single stress for me. So this is a function of sigma 1, sigma 2, sigma 3. Hopefully that's not off the board. That's close. All right, so what I've done, taken a hugely complex problem, simplified it, understood it, increased complexity, and then I've simplified it again, okay? So this is a process that we go through over and over again, but the cool part about simplifying it into this stress is now I can apply failure mode theories, okay? So failure modes, let's just call one is distortional energy. So we have a many, there's max shear, there's a bunch, but this one is really good for ductile materials. And I'm going to assume that my finger pad, I want it to be a little ductile because I want it to flex like a real finger would, right? Like skin. So I'm picking a distortion, failure theory that is good for a ductile material. Thus, I'm assuming I'm building this thing out of a ductile material. And basically what that says is that the safety factor is something we build in to all of our components. And basically that's a ratio of the yield stress. So let's say I'm using some carbon fiber 3D printed novel material that has some yield. So if I take that material and I pull on it, it's going to yield eventually, right? And I don't want my fingertips to yield, right? Because if they yield, then basically it's not going to work the same in future. I want this to last forever, right? So now I can take this sigma equivalent, and all of a sudden what I've done, this may look very simple, and that's why we love this, is all of a sudden now I've brought in material parameters. So this is a material parameter. And as mechanical engineers, we play with new and novel and classical materials all the time. So really what this is, if we just want to look at it graphically, is I have some yield of my material. Okay, so these are my stresses. I'm just going to say sigma here. This is my component stress, but I'm going to plot the max distortional energy theory. What it says is that we have a boundary region that looks like this. So again, this is my material region. This is defined by my material. And here is my stress on my component. And let's just say it falls right here, okay? So if it falls in this area, it's going to last. It's safe. It will not fail. If it falls outside this boundary, let's say it goes out here, my safety factor is 0 because I'm outside this boundary. My ratio, I'm outside of it. It's going to fail. Okay, so what I've done now is I've understood if my component is going to fail or not. And I've done that as a function of stresses. Stresses are a function of geometry, and that's where design comes in. So now I have the tools from machine design to design not only the geometry of my finger, but also the material selection built in here and a variety of things. And this is just the tip of the iceberg. I mean, this is all we can do in about 20 minutes. But then I can take this and I can move into, give me 1 second here. Got 1 minute, I'm going to use it. This was just an analysis of it statically, okay? That's not how fingers work. You don't just pick up something once. Now I can go from this space where I've had individual stresses, but now let's say this is time. This is my stress. Well, now what if my stress does this? So when I pick up stuff, I hold stuff, I let it go, I grab something really strong. How do I take this analysis or this loading regime and include it back into my design and failure analysis? Okay, so I think that's my 20 minutes. I believe I wasn't really watching the clock. I think that's my 20 minutes. But that's what we do in machine design. I'm going to just plug my other class real quick. I also teach a class called Finite Element. So finite element is we use computer simulations to basically do this. So let me just draw our fingertip again. So I looked at this. We just did this analysis. Thank you for your help. Well, that's great and all, but if I needed to do this for every single small detailed feature of this, well, what I would do is I would start using computational methods. So I would bring it into the computer space and use these same fundamentals that we teach in machine design, but I would do it in a computer model. And then I would compare my analytic solutions to my computational solutions to my experimental solutions. We would build it in our machine shop on campus. We would fabricate it in mechatronics. And all of a sudden, we've made a device that not only helps people, but in my mind is very, very cool from an engineering standpoint. Hey, I appreciate your time. As I said, I'm a CSU grad. I don't think you could find a better engineering program on the planet. So thanks for your time. We'll talk soon. I'll take any questions.
Yeah, so I think we have about 10 minutes. So thanks, Dr. McGilvray. That was awesome. I love you've got like really awesome handwriting, and like, man, you have a way of making it seem, I love the board and everything. I guess what
it was hard to learn to write backwards. No, I'm just kidding. I don't write backwards. It's amazing.
You're like really good at it. The one thing that I kind of want to say before we go jump into questions is I hope you as the participants can see the connection between all these classes now, right? And so you saw, like, I kind of talked about the numerical methods, computational piece, right? Dr. Roberts talked about geometrical dimensioning and tolerancing, and then Dr. McGilvray talked about some more of the design, and all these things you can kind of plug in together, right? So when he was talking about finite element analysis, that uses numerical methods that we kind of learn. So finite element analysis, you know, he relies on these types of computational methods that we learn. So all these kind of things all fit together, so you can get a feel for the things you learn here at CSU. But we have about 8 minutes left, and so yeah, I'd like to open it up to any questions that anyone has for the three of us. I think Dr. Roberts is still here too. So yeah, do you have any questions for any of us?
Don't be shy. Please speak up.
Nothing?
Well,
Really?
if you think of something, you can definitely look us all up on the website and just send us emails. We're happy to chat offline. If something comes up in the next 10 minutes after we get offline, you're like, oh, I wish I had asked this. Go ahead and feel free to hit us up.
Hi, this is Jackie here. I was just going to say, do any of our professors have advice for students looking to study engineering? So things that they can do now to prep either in high school or in the college classes they're currently taking?
Go ahead. Yeah, go ahead, Sam.
Well, so I guess I was under the impression that you guys are all high school students, right? Or is this, yeah.
And we might have some transfer students attending community college on the call as well.
Okay, cool. So what I would say for the high school students is get involved with your robotics clubs. If you have a robotics club at your school, those are fantastic ways to get your feet into engineering and actually get involved in some pretty high level design and programming pretty early. So if you're interested in that sort of thing, that's a really good avenue. For the transfer students, I think that taking courses, getting the calculus death march out of the way at community college would be a great idea, right? Take Calc 1, Calc 2, Physics 1, Physics 2, all those sorts of courses. I think would put you in a really good position. I think the one thing, and I think that the three of us, Dr. McGilvray, Dr. Roberts, and myself have tried to convey is that I hope you saw how excited we are about all this stuff, right? Like, this is cool. So like, dive into it, get into nerd stuff, start watching YouTube engineering nerd channels, right? Like, there's Smarter Every Day. That's a really good one. I think the more that you embrace this as something that's exciting and interesting, I think that would be really, really useful. So sorry, Kirk, I don't know if you want to add to that. Sorry, I cut you off there.
No, I think you hit it right on the head. The reason you're coming to CSU is to be trained as an engineer. So we give you all the skill set you need, but realize that what we're doing, whether you've heard about it or not, is all based on physics, math, science. And we are try to be good communicators. So English, writing, communication, all those skill sets, you can use all of those in engineering and be successful. So whatever you're passionate about, I think Dr. Bashara said that, if you're passionate about something, you can apply that directly to engineering in my mind. And you should just peruse our website. The stuff we do at CSU is so crazily breadth. I mean, there's such cool research going on that if you're like, hey, I want to be interested in the mechanical engineering science of agriculture, we have people that do that. I mean, there is something here that will make you happy in your career as an engineer. So just try to figure out what that is. And if you're curious, ask us questions. All us professors are here because we like engineering and we like talking engineering and we like educating the next generation of engineers. So do not ever be afraid to reach out to any of us and discuss engineering. That's why we're here. So that'd just be my thing. I was very timid as a freshman coming in to approach a professor, these almighty professors. That is not the case. I like talking to students. That's why we're here. We want to be involved. So take advantage of that.
And it looks like
And I
Eric
get-
asked in the chat, will I be able to, oh, sorry. Really quick, so Eric asked, will I be able to transfer credit from classes in MECH? Probably. That's a good question for our advisors. And so if you just contact so I sent a little link there in the chat for our people page. And if you scroll down, you can see the academic advisors and they'll be able to help you with specific transfer questions. Sorry, I cut. So okay, go ahead.
I have a question. Would you recommend taking at the community college different engineering classes, or should I save that till being at a full-time engineering program?
That's a really good question. And so that's one where it all depends on the transfer agreement. It's like, so the more classes you can take from community college, the better. I'm a product of community college. I went to community college before I went to university. It saved me a ton of money. I think it's a great idea. I was lucky in that there was a transfer agreement between the community college that I went to and the undergrad I went to. And so that helped a ton. And so the only reason I say that is it would be really unfortunate to take an engineering class at the community college and then have to retake it again at the university. Whereas you could have taken maybe like a, liberal arts credit or that sort of thing and kind of gotten that taken away. So I think the thing I would recommend is just contact those academic advisors and just ask them. They'll know. You could just say, I'm currently a student at whatever community college. I'm taking this class. Will this transfer in? And then they'll let you know really quickly if it will or not. But yeah, I think the more classes you can take at community college, the better for sure.
Cool. Thank you.
Yeah, no problem.
Yeah, and I would just say definitely reach out with those transfer credits because we're working to build out our articulation agreements with community colleges. So we want you to be, in touch with us and we can help you figure out any of those credits, definitely. So I dropped my email in the chat. My name is Jackie, by the way, and I'm the manager for undergraduate recruitment programs. So give me a shout if you need anything and stay connected throughout this whole process.
Sorry, Jackie, I should have introduced you. Yeah, go ahead, guys.
Thank you for your time today. This has been really fun to go through everything. And this is definitely both of our top choices as of now. We do have class starting in a minute, so we have to go. But it was really awesome to meet you and get to know you. And thank you for the lessons. They were very helpful. Yeah, your lessons were probably the most fun lessons we've had throughout all of our Zoom lessons on all of the colleges. So definitely big thumbs up. Thank you so much.
Thank you, guys.
Thank you.
Even better in person.
Right. I just wanted to ask if any students that are on the line are 16 years old or younger. That's mostly older students that are about to go into college or are already in community college. Okay. The only reason I was asking is because we also we are going to be running summer camps to allow students in the age range of 13 to 16-year-old to understand what engineering is all about, do some robotics, and I just thought I would throw that in as an opportunity to learn more about engineering.
Yeah, so it looks like we have one. So Eric is, so Eric, keep an eye out for that. Thanks, Dr.
Laney
Robinson.
was waving too, so it looks like we had two.
Oh, okay. Great. Yeah. So you might be interested in participating in one of our summer camps. And if you just go to Colorado State University Mechanical Engineering summer camps, you'll find information. We're still updating the information for the summer camps. They'll be happening in the first few weeks of June of this year.
All right.
Sorry, I should say June of 2021.
2021. There you go. Of this academic year. Yeah.
Yes, exactly.
Okay, cool. So I think our time is up. We were supposed to end at 12:10. I want to be respectful of everyone's times. So yeah, go ahead and check the chats for some information about the faculty listings, Jackie's email information, and some information about the summer camps. All those links are there. But if there aren't any other questions, thank you all for joining us. And like I think like Dr. McGilvray said, we're all here to help. So feel free to email us if you have anything else and anything we can help with. All right.
See you,
Thanks,
everybody.
Thank you so much.
Yep. Thank you.